Welcome to another explainer. Okay, let's dive straight into this. Today we are conquering what is absolutely, without a doubt, the most daunting challenge in the Cambridge Computer Science exams. Whether you are sitting for syllabus 0417, 0478, 2210, or even AS&A level 9618, you know exactly the moment I'm talking about. You turn the page of your exam paper, and there it is. A massive, intimidating 15-mark question staring right back at you, commanding you to write a complete program from scratch on a completely blank page. No integrated development environment, no autocomplete, no syntax highlighting. Just you, your pen, and the scenario. I like to call our winning strategy for conquering this the jazz musician. Now, you might be wondering, why a jazz musician? Because truly great jazz musicians can improvise beautifully, but they can only do that because they have completely mastered the underlying musical structures first. They know every single rule inside and out before they even attempt to break them or play around with them creatively. In the exam hall, we constantly see two common types of students who simply haven't mastered this underlying structure. First, there's Alex. Alex is the overloader. Alex memorizes every raw computer science fact, every syntax variation, and every complex algorithm, but has zero strategy for analysis. When Alex sees a blank page, they just throw every single loop, array, and nested if statement they know onto the paper, hoping the examiner will find something worth grading. It's code soup. It has no logical flow. Then, on the other end of the spectrum, there's Sam. Sam gets overwhelmed, panics, and totally rushes the code. Sam completely misses the specific command word requirements hidden in the scenario. Sam loses easy, guaranteed marks on fundamental things like variable declarations and input prompts because they didn't stop to decode what the question was actually demanding. Today, we are going to fix both of those deeply flawed approaches. We are going to build a structured, robust architectural blueprint directly on proven Cambridge strategies so you can confidently tackle any programming scenario they throw at you.
Here's our syllabus for today's explainer. We are going to follow the natural chronological timeline of an actual exam setting to guarantee your success. First, deconstructing the scenario. Second, the four main components every single program must have. Third, planning your program logic before writing. Fourth, actually writing and commenting your code. And finally, running through the ultimate mental checklist to secure those final marks.
Let's start right off with step 1, deconstructing the scenario. This is the moment we shift your mindset from being a panicked student rushing like Sam into becoming a methodical, calm software architect.
The source material for this explainer highlights an absolutely crucial concept. In large commercial tech companies, teams of designers and programmers work together to build massive applications. They don't just open a blank file and start typing. The complete system is broken down into highly specific individual tasks using what we call a top-down design process. Different programmers handle different parts. One person handles the database login, someone else handles the user interface, someone else writes the search algorithms. Now, obviously, you are sitting in the exam hall working completely independently. You don't have a team of developers backing you up. But applying this commercial top-down design method is the absolute secret to making complex exam tasks manageable. You have to act as your own project manager first. You must break the big, scary 15-mark problem into tiny, bite-sized, easily solvable pieces before you write any code.
And this brilliantly illustrates the exact workflow you need to adopt. Break down the task, select your programming approaches, combine them for a complete solution. A top-scoring exam solution isn't one giant, miraculous stroke of genius. It is simply a combination of smaller, well-understood individual programming elements stitched together logically. If you know how to write an input prompt and you know how to write a simple while loop, you literally already have the building blocks. You just need the framework to connect them. And hey, before we continue and dive into the exact framework that connects all this, subscribe to our YouTube channel, Ace the Exams, at acexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. It really helps us bring you more of these deep dive strategy sessions.
All right, that brings us to section 2, the four main components. To break down any scenario successfully, you need an anchor. You need a system. We use the ISPO framework: input, storage, process, output. Let's unpack this framework and see exactly how it maps to decoding your exam paper and targeting those specific assessment objectives.
Component 1 is input. This is the data required by your program to get things moving. It's the starting line. Now listen to me very closely here, because this is exactly where a student like Sam always loses crucial marks. If a scenario question involves inputs, the text will describe exactly what is expected. But the golden rule, the one you must never, ever forget, is that any inputs described in the question absolutely must be validated as part of your code. If the exam command words tell you to prompt the user for an employee ID that is 6 characters long, you cannot just write input employee ID and move on to the next step. You must immediately follow that input with a validation loop to check that the data is actually 6 characters long. If it's not, you reject it. Examiners are specifically hunting for your ability to protect the system from bad data.
Component 2 is storage. This means setting up your data structures, your variables, constants, and your arrays. So the crucial point here is paying forensic attention to the exam prompt. Exam questions will frequently mandate specific variable or array names. For example, they might explicitly tell you to store the data in an array called empdata. You must use these exact names. Do not invent your own. Remember our top-down design approach we just talked about? In a real-world software team, if you name a shared variable differently than your teammate, the entire codebase crashes when you try to combine it. Cambridge examiners are testing you on this exact commercial discipline. When you are reading the prompt, physically highlight the required names with your pen and copy them exactly into your pseudocode. Case sensitivity matters, spelling matters.
Component 3 is process. This is the heavy lifting. This is the engine of your code. This is where the input data is manipulated to calculate averages, find highest and lowest values, or search for a specific match in a database. The key to processes is following the conditions laid out in the scenario exactly as written. Don't be like Alex and overcomplicate it with unnecessary nested loops. Also, this is where the PEEL framework, point, evidence, explanation, link, comes into play when you have to answer written theory questions about your code. When asked to explain a process, you make your point about what the algorithm does, provide evidence from your code snippet, give an explanation of the logic, and link it back to the scenario's requirements. But for writing the actual code, just follow the math. If the question indicates a condition of greater than or equal to 50, you need to code precisely greater than or equal to 50. If you just write greater than, you literally drop the mark because your logic is flawed at the boundary. Decode the command words carefully.
The final component is output. This is what your program actually produces for the user. The required outputs will be fully described in the question, but the examiner is looking for something very specific here. Meaningful messages. You should never just output a raw variable on its own. You need to use string concatenation to clearly present the values in a user-friendly way. Instead of just writing output salary, you need to write output current salary, salary. It makes your code professional, it shows empathy for the end user, and it tells the examiner you deeply understand the full computational experience. Stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to at acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions.
All right, let's move to Section 3, Planning Program Logic First. This is the crucial bridge between reading the question and writing your final answer on the page.
I really cannot emphasize the truth of this quote enough. It is best practice to plan the logic of the program before you write a single line of actual code. Think deeply about why planning is so absolutely critical in this specific context. In the exam, you are writing pseudocode or program code by hand. You do not have an IDE, an integrated development environment, running in the background to magically highlight your syntax errors in red, or to pop up a warning that you forgot to declare a variable. You are flying blind. Spending 3 to 4 minutes sketching a quick logical plan in the margins prevents you from realizing halfway down the page that you completely missed a crucial loop, which would force you to scribble everything out and waste massive amounts of time.
Let's jump into an interactive workshop right now. Challenge number 1, data scan. I want you to look at a practical example from the source material. Imagine we have an array of 50 employee IDs and we need to let a user search for one. Look at how beautifully simple this plan is. Step 1, obtain and validate the user input. Step 2, loop through the array to search for that specific ID. Step 3, within that loop, output the data if a match is found. Step 4, output a not found error message if the ID is nowhere in the array. This takes maybe 30 seconds to scribble in the margins of your paper, but it guarantees your final program will have a perfect, logical flow. Alex would have skipped this entirely and just tangled up 3 different loops until the code was unreadable. Sam would have rushed, done steps 1 through 3, and forgotten step 4 completely, losing the final error handling marks. We are going to follow the plan.
Okay, that takes us to Section 4, Writing and Commenting Code. This is where the transformation happens. This is where we execute. We are going to translate our carefully laid out plan into high-level, point-scoring pseudocode.
Let's analyze this code snippet together for Challenge 2, Find the Flaw. Well, actually, there are no flaws here. This is exactly what a top-tier answer looks like. Let's break down why. Look at the very top of the structure. What do they do first? They declare their variables. Declare search ID as string. They also smartly leave a little bit of physical blank space on the paper just in case they realize they need another variable later on. Then, notice the comments, // input and validation of ID by user. Listen, commenting isn't just a nicety or a polite thing to do. It explicitly explains the logic of your algorithm to the examiner reading it. If your code syntax gets a little messy under pressure, a crystal clear comment can actually save you marks by proving you fully understood the computational thinking required. Next, look closely at the validation loop. While search ID equals empty or length search ID is equal to 6 do. This is brilliant. It perfectly addresses a scenario rule that an ID must be exactly 6 characters and cannot be blank. It forces the user into a loop, prompting them again and again if they mess up. It makes the program completely robust.
Now for Challenge 3, Speed Writing. We move to the core search process. This slide brilliantly illustrates how to deploy a repeat until loop effectively. We start by initializing a counter. Declare counter integer less than 0. We also set up a Boolean flag, which is a massive pro move. Declare found Boolean false. Inside the loop, we use an if statement to check if the user's search ID matches the employee ID array at the current counter index. If it does match, we output the requested data, and crucially, we flip our found flag from false to true. Then we increment the counter by 1. And finally, look at the exit condition, until found equals true or counter equals 50. Why is this logic so brilliant? Because it is fiercely efficient. If the employee we are looking for is found at index 5, found becomes true and the loop stops immediately. It doesn't needlessly waste processing power searching the remaining 45 records. This understanding of algorithmic efficiency is the exact difference between an average grade and a top-band grade. And of course, at the bottom, we have our fallback. If found equals false, then output our error message, neatly completing step 4 of our top-down plan.
Finally, we enter Section 5, Checking and the Final Checklist. You've written the code, your hand is cramping, you're exhausted, but we are absolutely not putting our pens down yet. You must rigorously proofread your code because, again, you have no compiler to catch your human errors.
Let's rapidly fire through the most common pitfalls that examiners see every single year. These are guaranteed mark losers that you can avoid. First, simply forgetting to declare your variables at the top of the program. Second, misspelling the names of the arrays or constants that were explicitly provided in the question. Third is a massive one, starting or ending into loops with the wrong numerical value. In Cambridge pseudocode, arrays are typically 1-indexed, but sometimes in specific language contexts they are 0-indexed. You have to trace your loop. If an array has 50 items, and you start your loop counter at 1, but it's a 0-indexed array, you completely miss the first piece of data. If you end your loop at 49 using a strictly less than symbol, you miss the last record. This off by 1 error destroys exam scores. Fourth, using incorrect logical operators. Imagine if you used an AND instead of an OR in that validation loop we just looked at. The logic would literally be impossible to satisfy and the program would crash. Take a deep breath and manually trace your code. Pretend you are the computer.
I want you to memorize this exact table. Take a screenshot with your mind right now. This is the Computer Science Success Blueprint. This is your ultimate mental checklist. Variables. Did I use the provided names? Are my types correct? Inputs. Did I validate every single piece of user data? Processes. Are my algorithms efficient? Did I choose a while loop when I should have used a for loop? Outputs. Are my messages clear and concatenated correctly? Other. Did I comment my code to explain my logic to the examiner? Memorizing these questions is the best way to secure every possible mark before handing in your paper. And listen, the data speaks for itself. Students who implement these computer science strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCS to excel in your Cambridge examinations. Subscribe right now to acetheexams_IGCS and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for computer science and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams. Your Cambridge success starts here.
I want to leave you with this final provocative question as you prepare for your paper. Does your code tell a complete logical story from input to output? Remember our jazz musician analogy from the very beginning. You absolutely cannot improvise a brilliant 15-mark solution without mastering the scales and the structures first.
Use the ISPO framework to break the scenario down into manageable pieces. Plan your logic out in simple steps before coding. Write carefully, declare your variables, use efficient loops, and then run every single line through your mental checklist. I hope this gives you the exact blueprint you need to conquer the blank page. Keep practicing, stay logical, and I will see you in the next explainer.